Hello, everyone. My name is Luis. I am a PhD student at the Technical University of Darmstadt. In this occasion, I'm presenting our paper titled Stay Connected, Leave No Trace, Enhancing Security and Privacy in Wi-Fi by Obfuscating Radiometric Fingerprints. Let me start saying that the omnipresence of Wi-Fi devices in our current society demands for stronger and more reliable security and privacy mechanisms in order to protect us, users, from potential adversaries. Traditionally, Wi-Fi security has been implemented above the physical layer. For instance, in the network layer, application layer. However, security can be increased by using physical layer characteristics, also referred to as radiometric fingerprints. For instance, we have hardware impairments or specific channel features that would allow us to for another degree of authentication. In this paper, we refer to radiometric fingerprint as a signature inherent to the RF circuitry. This signature that appears by default in any transmitted signal is caused by imperfections of the hardware. These imperfections manifest in the form of negligible but still distinguishable errors. Such degree of uniqueness shows the potential of radiometric fingerprints to improve authentication and security. However, it also raises concerns with these two aspects. In order to address privacy and security issues in Wi-Fi, we propose RF veil. RF veil enhances the user privacy by concealing the radiometric fingerprint of the device from potential adversaries, while still allowing fingerprint-based authentication at legitimate receivers, with the objective of strengthening security. The proposed solution, RF veil, is devices crafted pseudo-random phase noise that is added to the transmitted signal at the transmitter in order to conceal or obfuscate the radiometric fingerprint and without impacting the communication quality. The proposed solution has the following properties. It can preserve privacy, it can improve security, it has low overhead, it's scalable, and in addition, it allows coexistence between RF veil and non-RF veil devices. Within RF veil, we have two branches. One of them is privacy preserving only, and the second one adds another degree of security. You can find out more about this in our paper. The contributions of this paper are the following. First, we show the vulnerabilities of recent radiometric fingerprinting solutions to impersonation and tracking attacks. In this paper, we deal with channel state information-based fingerprint solutions. In addition, we devise RF veil, which is a fingerprint obfuscation framework that circumvents the privacy issues and improves security. To achieve this, we propose a method on injecting artificial noise to the fingerprint. So we hide the fingerprint from potential attackers and prevent them from extracting it, but we also guarantee that the communication quality is not impacted. And we also design RF scope, which is a benchmarking tool that is used to assess the effectiveness of radiometric fingerprint obfuscation schemes against statistical attacks. So in Wi-Fi, the channel estimated at any subcarrier is given by this first expression here. So the channel is the actual channel plus some perturbation, and this perturbation is essentially a WGN noise. If we assume the high SNR regime, we know that this noise is negligible, and basically we can have an accurate estimation of the channel. that we can decompose in modulus and phase. So this research, this paper is based on CSI fingerprinting, so specifically on the phase. So if we can further decompose the phase into other phases, into a subset of phases, and this is given for this is true for every subcarrier. So this phase, this CSI, consists of linear phases, or that we call linear errors, linear phase errors actually, and that depend on the time of flight, for instance, or the channel frequency offset. And these errors can be filtered out. We can remove them because they are linear and they change for every subcarrier, and we can get rid of them. However, there's also a component that is nonlinear, and this nonlinear is the fingerprint. The fingerprint, that is the additional signature that is added, or that is by default included in any transmitted signal from a receiver, from a transmitter. To show you how unique these fingerprints are, so these are the phase essentially that we can measure in radians or degrees. And in my example, I showed you 5 different signatures, 5 different fingerprints that belong to 5 identical devices, 5 smartphones that belong to the same series, same manufacturer, so they all have the same hardware specifications. Nevertheless, the fingerprints, although they resemble to each other to some extent, they are different. And this difference allows to differentiate one device from the other. So it has the potential to, let's say, improve security, authentication, security, but this can also be exploited by adversaries for malintended purposes. So we will analyze, so we will study 2 different kind of attacks, attack on security and privacy. But before we explain those attacks, I'm showing first the adversary model, where I have a legitimate user, the client, that is communicating with a access point, in this case, the receiver. So we could assume that they built a solution based on fingerprint authentication. However, we may also have an adversary. It could be close to the user, close to the receiver, or somewhere in between, that is also capturing this information. It's capturing Wi-Fi frames. And if we assume that this is a smart adversary, it can decode, it can obtain, extract the fingerprint from those captured Wi-Fi frames. So essentially, the Wi-Fi frames are obtained, and the CSI is extracted, and then from the CSI, after filtering out, filtering out the nonlinear or the linear phase errors, we can obtain the fingerprint. And knowing the fingerprint, so we evaluate 2 kinds of attacks. Or the first one is we have the adversary that is sniffing encrypted traffic, is extracting the fingerprints from the channel state information, and then is recording the activity time of the device. So we have 2 types of bars here. So for 5 phones, and 2 kinds of bars. So a volt bar, that is the actual connection time of the device, and the predicted time. So we see that the adversary can identify almost very accurately when the device is connected or not. So, and certainly this is a infringement of privacy. And we know that there exists MAC layer anonymization techniques, but this cannot prevent adversaries from these kind of attacks because these are implemented in the MAC layer. Nevertheless, this feature is obtained from the physical layer, right? The fingerprints. We also have a different attack, which is an impersonation attack. In this case, we assume that the adversary has extracted the fingerprint. So we assume, again, a smart adversary where it can modify its own fingerprint. So the adversary is aware of its own fingerprint. Now it has extracted the fingerprint of a legitimate user. And because the fingerprint is based on essentially on the CSI or in the CSI phase, the attacker can adapt or modify its fingerprint by adding phase rotations to its own, to every transmission. So it mimics a transmission as if it were from the legitimate user. And we observe that this red dot is an adversary, and we have receivers at each of these blue dots. And we can observe that, that for several locations close to the adversary, the impersonation attack, the impersonation success is quite high, above 98%. This is true for, we evaluated two frequencies, 2.4 and 5 gigahertz. And then for distances that are farther, this success decreases, but essentially it's due to physics, due to the propagation environment that does not allow, I mean, we received the Wi-Fi frames with errors, and sometimes it was not possible to decode or the data itself, or also the signature. So we can see that indeed it is possible, feasible for an attacker to decode, to impersonate a legitimate user. So here we are dealing with advanced attackers, in this case, and the one that can adapt its own fingerprint, and also here one that can extract fingerprints and attract several users. So in order to counter these issues, we propose RF-Veil. And RF-Veil is based on adding or obfuscating the radiometric fingerprint. So in this first block, we have the transmitter of a legitimate user. The legitimate user has its own fingerprint. And now by means of a synchronization index and a key, we generate a sequence of random numbers that are mapped to a phase rotation, to a perturbation. This perturbation is added to the original fingerprint of the device, and we end up with a randomized fingerprint. The objective is, of course, to conceal the fingerprint of the user such that if the traffic is sniffed by an adversary, the adversary cannot recover the original fingerprint and then use it for tracking or impersonation. So and now at the receiver also needs the synchronization index and the key in order to generate the same sequence of random numbers. So also the receiver will obtain the CSI. From the CSI, it obtains the phase. As I showed here, excuse me, here, the phase. And once the phase is obtained, then in the phase we have linear errors, we have the fingerprint, and we have an additional perturbation that we have added. So from the CSI, we remove the additional perturbation, then we end up only with the linear and non-linear error, and the non-linear error is the fingerprint. And from here, we filter out the linear part, and finally, we obtain the fingerprint. So by means of this procedure, we can protect the fingerprint of the device and prevent attacks. Of course, what is needed is this synchronization index in order to always generate the same sequence of phase rotations at the transmitter and receiver. And this is the additional overhead that I mentioned in one of the slides at the beginning, because this data needs to be exchanged such that we can reproduce the same sequence of phase rotations and denoise the obfuscated CSI. So RF-Veil, this solution can preserve communication quality. We compared standard Wi-Fi with Wi-Fi implementing RF-Veil. We compute, we obtain the throughput at different distances, 2, 5, 10, and 20 meters for different modulation schemes, 64 QAM, 16 QAM, QPSK, and BPSK. And we show that the communication quality, the throughput doesn't change. There's a small overhead, as I mentioned, due to this key exchange. And this is why we see sometimes small variations here, as you can see, specifically in the QPSK, where the throughput is significantly lower. But essentially, this is a small price to pay in order to get to have a higher privacy and security. One important aspect here is how we devise, how we obtain these phase rotations. So we realized that if we use a naive randomization, and smart attacker, although the fingerprint is obfuscated, is changed, and smart attacker can perform a denoising attack, something that we call statistical attack, by collecting a number of Wi-Fi frames. And we see that it is possible for a smart attacker to get rid of this additional error and obtain the original fingerprint. So designing these phase rotations is also a direction that we investigate in our paper. So let's say for zero mean distributions, we call them, when we use zero mean distributions, we call this a naive randomization. So essentially, MAE means a mean absolute error with respect to the original fingerprint. Here, just showing the error of the recovered fingerprint with respect to the original fingerprint. And we compare we show the error for a different number of samples, where this number of samples is essentially the number of Wi-Fi frames that the adversary has captured. And so we see that for a small number of frames, the error is quite high. Nevertheless, if the adversary is capable of collecting more frames, this error decreases to almost zero, and for different kind of distributions. And 10K samples is something that an adversary can collect in 2 to 5 or 2 to 10 seconds, depending on the rate. And so we don't see this. This is quite possible. I mean, 2 to 5 seconds is feasible, and the adversary can recover the fingerprint with almost zero error, as you can see here. So in order to thwart these kind of attacks, we propose properties of probability density functions that probability density functions should have in order to prevent this kind of behavior, in order to prevent an attacker from recovering the fingerprint. So with RF-Veil, we also evaluate these same kind of distributions. So by the way, this parameter means the variance of the distribution, denotes the variance of the distribution. And we see that even though an adversary can collect a large number of samples, the error does not go down. It's actually quite high, 13 degrees. And this can therefore improve privacy and security by not letting the adversary extract the true fingerprint. So in this paper, we have exposed privacy and security vulnerabilities of radiometric fingerprint solutions, and we also devised practical methods to resolve them. Radiometric fingerprinting is typically considered a secure method for device identification. However, we show that radiometric fingerprints can be used to mount impersonation attacks and also tracking attacks. We illustrated that naive randomization does not withhold adversaries from mounting attacks, especially if we deal with advanced attackers. And therefore, to solve these issues, we devised RF-Veil, which can preserve privacy and prevents impersonation attacks. So you're welcome to read our paper. You can download it from this address. Thank you for your attention.